Can you hear me?
Yes.
It's very good. Can you hear me? Is good sign. We're in business. So I haven't given you the assignment yet, but we'll maybe today, end of the class. And we completed, I think, chapter 0, 1, 2. Yeah, we haven't started the chapter 3 yet. Okay. We start chapter 2, I think I should talk about the let's do the attendance first. And then attendance. First. Now we have a different attendance. One moment. Yep. Right, Saturday is 9. So we missed one class because of the vacation. The first name I have is Angel Antunes.
I'm here.
Very good. Next is Arsani Atalla. Are you here? Arsani Atalla? No. Charlie Ben.
Here.
Robert Boese.
Here.
Philip Chen.
Here.
Jimmy Cheng. Jimmy Cheng. Not here? Not here? Okay. Alyssa Chi.
Here.
John Cubas. John A. Cubas. Not here? Ankara.
Present, sir.
Jill Diora. Jill Harish Bhai Diora. No? Okay. Trevor Eckler.
Here.
Jair Estrada. Are you here? Jair Estrada? No. Praise Yubani.
Here.
Stephen Hong.
Here.
Christian Cortez.
Here.
Antonino Indondoli.
Here.
Anish Kadaka.
Here.
Ayush Kaul. Sudeep Ramecheni. Matthew Lasirona. Matthew Robert Lasirona. Not here. Kenneth Leong.
Here.
Kenneth, okay. Melody Long.
Here.
Ricardo Lopez. Pragati Makani. Pragati Makani. Yeah.
I'm here.
Philip Martinez.
Here.
Good to you. Jen Maxwell.
Here.
Good to you. Sean Ng. No. Sean Ng. Sue Lam Ng. She was here. Sean is not here. Scott Nguyen.
Here.
Shen Nguyen.
Here.
Dylan Dylan Pam.
Here.
Ayush Ramani.
I'm here, sir.
Luis Ramirez.
Here.
Eric Rodriguez.
Here.
Eduardo Ruiz.
Here.
Andy Shi. Shy. Andy. Okay, got it. Young So.
Here.
Dylan Suen.
Here.
Johnny Tram.
Here.
Akash Thiagarajan. Akash, are you here?
Oh, I'm here.
Nicholas Thomas.
Here.
Nicholas Thomas.
I'm here.
Jonathan Beladares.
Here.
Jonathan Vargas. Stephen Vasquez.
Here.
Rita Velasco.
I'm here.
Jia Cheng Wen.
Here.
Anthony Yu.
Here.
Ji1 Yu.
Here.
Justin Yu.
Hello.
Okay. Anybody missing? Or showed up late or anything? No. Okay, done with it. Done.
Sir, I just wanted to check if you got.
Now, so we covered only that the conversion stuff, binary to decimal, decimal to binary, hexadecimal, binary, decimal, hexadecimal, kind of stuff. So today we'll start a new chapter. I think I'll give you the assignment. Do you have any question about the conversion? Or we have? Very good.
Professor, I don't really have a question, but I might want to let you know that I got to class late.
Jair?
Yeah, that's Jair Estrada.
Okay, let me get your attendance in order. Just link. Yeah, got it. Okay,
Thank you.
no problem. So from those past couple of chapters, 0, 1, 0, 1, 2 or something. I think 0, 1, and 2. No, I haven't done chapter 2 either. Yeah, no, right. Okay. Let's go through chapter 2 first. Let me check whether it is open for you, the PDF. Chapter 2, I think it's open. 3 is not open. Okay, 2 is open. Let's go through the chapter 2, and I'll give you the assignment. Let's share video. Okay, can you see my screen now? Is chapter 2, basic computer operations and assembly language programming. That's the PDF heading. Components of a computer, we learned somewhat, but to a little detail. Programmer's view of computer system. Then we learn about MIPS, the simple program translation with MIPS. MIPS is million instruction per second. Allocating variables to registers, arithmetic statements, if-else statement, for loop, while loop, do loops, input, output, that kind of stuff. And it's from the book Peterson and Hennessy, 1.1, 1.5, 2.1, 2.3, 2.6, and appendix 9. So we learn about these types of computers: server, desktop, laptop, and embedded system. I actually had a vaccine for the corona vaccine, the booster dose. Essentially, they're the same dose, it's extra. And I don't know, it's going to help much or not, but I'm feeling a little bit of a body ache, kind of not very good feeling. Huh? I had like 11. I already have a couple of Tylenol in case I want temperature. All right, so types of computers, servers, desktop, laptop, embedded system. We talk about that, but I have some question on that actually. So anybody remember what is a server? What makes a server? Anybody remember?
It serves to the other computers all around the world or the area.
Say it again, I couldn't hear it properly.
I mean, those are like the big computer or the processors. They serve in helping like passing the networks and things with other small computers, like personal computers in our home.
A vague answer. It's not very clear. So the server, so a home and computer, that's kind of a host, like a client. But you can make it a server if you have server software. So basically, what makes a server is the server software. So you have to install server software, and normally server machine has a little bit more power, like CPU power or hard disk, RAM, everything is higher capacity. And you have to install, say if you have a machine with higher capacity of CPU and also hard disk, also RAM, but that doesn't make a server. So you have to have a server software installed to it. And then, of course, you need to have a dedicated IP address to make it a server and use it as a server. So that's the main point and main difference between server and host or client. So your laptop, desktop, and smartwatch, all that is a host, a client. So you can connect to the server and get information. So there are lots of servers. You can have Windows Server, Linux Server, Mac iOS Server, and then you have this. Then you have file server. Can be file server. So those are the things you can share. You can serve a client. It's compared to like a server in the bar. So they'll serve drinks to anybody. So anybody is a client, but then server is a specific person. So it serves 10 clients, 100 clients, that kind of thing. So client server. So server can serve the client's request in terms of computing as well. So that's the main difference. And then you have, you understand laptop, desktop, all that stuff. Then all have similar components like central processing unit and memory. You need to go share again. So you have memory and other storage and input-output devices. We already learned about that, what input-output device, display, keyboard, mice. Keyboard, mice, display, there kind of display can be input device, can be output device. So how it can be input device? If it is a touch screen. And then keyboard is input device, mouse also input device. All right, then right here. So this is the under the hood. When you open up the keyboard cover thing, it shows up this kind of diagram is there. So you have a hard disk, hard drive, processor. You have a pan with cover, spot for memory, DIMMs, those the memory, the RAM actually. And then you have a spot for battery, motherboard, call it motherboard, the main board, pan with cover, and then DVD drive. So that kind of thing you can see when you rip off your laptop or desktop. And Programmer's view of computer is different. So you have central processing unit. Under that, you have a control unit and you have registers. Program counter, arithmetic logic unit, ALU. And they have a main memory on the other side, the RAM actually, the random access memory. Or can be hard disk called also memory. Then you have a system bus, is like a connector, and then you have the input-output devices attached to that. So this is basically the programmer's view of the computer system. So the registers also have memory, fast memory actually. We'll learn about registers a little more. The MIPS computer has 31 or 32 registers, 32 registers from 0 to 31. Shared set of wires that, so this is the definition. What is the system bus? Shared set of wires that connects components and provides communication. So you need to kind of memorize this definition. You may have a short question in the quiz and also in the midterm and final exam. Short question. So system bus is the shared set of wires that connects components and provide communication. Plus the communication channel basically. And input-output devices allow system to talk to outside world. Storage, hard drive, solid state drive. Communication, monitor, keyboard, mouse, microphone, earphone, speaker, USB, network card, Wi-Fi. They're all communication device. So you communicate with the computers through those. Central processing unit. This is main active part of the system, like a brain of a computer. Some CPUs, example, Sun, Spark, PowerPC, Intel x86. For this course, we use MIPS CPU, Silicon Graphics. We learn about that more, how to design it, all that, because it's simple. A recent processor, AMD Barcelona, 4 cores. That's how it look like, AMD Barcelona processor. They have core 1, core 2, core 3, core 4. Then we have the memory, cache memory, L1 cache, L2 cache, L1 instruction, all that stuff. Main memory, what is it? Main storage for programs that are actively running. So main memory, basically the random access memory. When you run the program, it stores data there and do stuff. There's also volatile memory. We learned that because when you turn off, it goes away the data. It's not there. And it uses bits and bytes. So nibble is 4 bits and byte is 8 bits. Half word 16 bits, word 32 bits, double word 62 bits. That's how they count. Now MIPS CPU, central processing unit, each memory address is 32 bits. So each memory address has 32 bits for the MIPS memory. And also they have 32 registers actually. We'll learn about the registers very shortly. Memory is a byte address. So each increment of address refers to the next byte. So 1 byte is like 32 bits and 8 bits. And if you go to the next byte, that's the past 8 bits. How memory hardware works. Memory is like an array of variables. Array of variables. First, we have to choose a location, array, specify the index, memory, specific memory address, mem_addr. Just a symbol. So you have, so the memory is like a series of array, so you can put things in it. So each array is like 32 bits. And a read, write, memory read, plus address bits on address pins. Set read control to 1, data appears on data read pins. Memory write, the reading and writing, how it happens. Plus address bits on address pin, plus data on data write pin. Set write control to 1, data gets written to location. That's how memory read and writes. This is steps. Memory viewed as an array of bytes, so you have a address and contents. And these are the hexadecimal numbers, those contents and the address. So you see OX in front of it. Basically, the hexadecimal number. Okay. Memory viewed as an array of 30 bits, as I mentioned here. So address, contents, like that. Keep going. Memory byte order. MIPS memory is a big endian, meaning that the byte with the lowest address is at the most significant end. Leftmost end with highest value. That's a big endian, and the leftmost is highest value. So it starts from 0 and go to the left with more value. Most commercial CPUs are big endian, so most of them are big endian, so same as MIPS, except Intel x86 and the little endian. Contents of a byte address, contents of a byte at address, OX000006. Right, so contents of a word at address that, this is from the picture actually, so aligned versus misaligned. If a word in a memory is aligned, the 4 bytes within the word do not cross word boundaries. So we have 4 bytes because it's 30 bits in one line. If a word is misaligned, it's 4 bytes cross word boundaries, so they go over. So it's like overflow. How to tell if a word address is aligned? Look at least significant rightmost digit. Look at least significant 2 bits. Divisible by 4. What is divisible by 4? Then is aligned. Size of memory address 30 bits. MIPS Pentium. Determine the amount of memory that can be addressed by programs running on CPU. Okay. 32-bit address means a program can see 2 to the power 32 bytes, and that's 4 billion something. 2 to the power 32. Note, for memory, 1 kilobyte is 1024 bytes. It's 2 to the power 10. Okay, so that's 1 kilobyte. Not 1000, it's 1024. 1 megabyte is 2 to the power 20. Here's the number. Gigabyte 2 to the power 30, and terabyte 2 to the power 40. It's a big number. So if you learn more about that, you can Wikipedia, terabyte, you'll see that. The difference between standard SI, International System of Standards, and binary uses. Standard SI is used for hard drives and other storage devices or data transfer rates. Binary uses is for memory. Many computers today have 64-bit memory address. That's Intel x86 running 64-bit. However, this does not mean that they all have 4 exabytes, like 4 times 2 to the power 60 bytes of physical memory. Okay, in the hardware. So later in the semester, we'll talk about virtual memory. Learn about virtual memory and application to this more memory than physically available. Learn about those. Parts of the CPU. Already seen that. Control unit, main active component in CPU. Arithmetic logic unit is the calculator where the calculation happens for CPU. Registers, you remember this, small passed memory inside CPU. So that's the definition of registers. Small passed memory inside CPU. That's the registers. And program counters, another definition. Special registers that contains address of the current instruction. It's kind of a pointer. If you heard about C++ or C actually, the pointer system. This is kind of a pointer, a special register that contains address of the current instruction. Program counter. MIPS has 32 registers, each a 32-bit word. We told you already. So it starts from 0 and go up to 31. So $0 means register 0, the first one. $1 is register 2. It's not really a dollar, it's not money, but it's the sign they use, it's a symbol for registers. So in this course, when you see that dollar something, means it's a register. It's not a money dollar. It's not US dollar or Singapore dollar or anything like that. 2 registers with restricted use. $0 is the first register, is 0, and equivalent to 0, and then $1 reserved for MIPS assembler. Do not use this in your program. $0, $1, don't use them. It's just a special use. Now, registers have alternate names. It's important. $2 to $3, like from second, third, and fourth registers, also called V0, V1. And then port 4 to 7, also called A0, A3, so address register. $8, $15, also called T0, T7. $16, 23, also called 0 to 7. And 24, 25, 8 and 9, T8, T9. 26 and 27, also called K0 and K1. And 28, also called GP and graphic pointer, something, stack pointer. And 29 also called stack pointer, like SP, stack pointer. 30 also called S8, and 31 called RA. Now use $0, $8, let's say for $T0, T1. So you can see that from $8 to 15 to $T0, T7, they are temporary registers. So when you do store something in temporary variable, so that's the temporary register T0, T7, and then 24, 25 is T8 and T9. So we can use them alternatively with the name. Okay, so don't get surprised if like $16, we just write $0, they're the same thing. Okay, so when you talk about function calls, so high-level language program and assembly language program. High-level language, we call it a statement, like one line. And assembly language, we call it instruction. Instruction 1, 2, 3, statement 1, 2, 3 in high-level language. So that's the difference, assembly and. In von Neumann architecture, programs and data are stored in the same memory. Instructions are executed in sequential order, except for branches and jumps. So we learn about branch and jumps, like condition if, then else statement, that kind of thing. What happens when a user runs a program? User types a.out/n, CPU finds the output file, and CPU loads memory with program code and data from file. Typical assembly language format is different. The operation, operand 1, operand 2, operand 3, like that. Operation, what the instruction does, was addition or subtraction, operand, then have variable. Operands is the variable. Operand 1, operand 2, operand 3, they're variable. And operation is the sign, what you do. Variables are allocated to registers if possible. So can also allocate variables to memory, slower. For example, contain integer variable. We have $S0 and $S3. So in a normal language, if you have variables, what do you do? So you have a variable S0, you put variable S1 plus S2 equal to S0. You want to do some addition. But here, to do the addition, you just write add, ADD, and you put the $S0, comma, $S1, comma, $S2. It means actually $S0 equal to S1 plus S2. And subtraction, same thing, put $S3, S1, comma, S2, meaning S3 equal to S1 minus S2, meaning that first one, second one minus third one, actually, first one minus whatever in the first register minus second equal to S3. So that's how it goes. S3 equal to S1 minus S2. Dealing with constants. How do you deal with constants then? So this is the variable. And then dealing with constants, at I is at immediate S0, comma S1, $S1, and 1 means S0 equal to S1 plus 1. So it's add immediate, they call it ADDI, add immediate is a operation, and this is the way you do that. S1 plus 1 equal to S0. So you write like this. It's 0 first and then S1 and comma 1. So there is no subtraction immediate. Instruction to program translation, MIPS, is a load store architecture. This means arithmetic logical operations work on operands in registers only. Load store instructions copy operands between registers and memory. So when you say load, it takes information from memory registers, and when it's a store, it puts register to memory. So this is the load store instruction. A good compiler will try to allocate frequently used variables to registers. So that's the thing. So if you have a variable that you use frequently, that's when you put that in the register, because the register is fast, small memory. Advantage. What is the advantage of registers? Fast access, less code. Disadvantage. May not have enough registers for all variables because you only have 32 registers. Must keep track of where each variable is. That's another challenge as a programmer. Okay. Now, so as you understand that the assembly language use symbols. So it's not English-like language, so use symbols. So these are the symbols: add, sub, and the dollar is a symbol for registers. Add I, add immediate is a command. Now, this is important, and then we have this example. First MIPS program. Let's say in C, you have this integer, b equal to 0, comma, w equal to 1, comma, x equal to 2, comma, y equal to 3, comma, z equal to 4. So we have all these variables. We declare it. We put a semicolon after that in C. And then int main void, because it doesn't return anything, this function. And then you have a curly bracket, and then you have this w equal to z, v equal to w plus z, y equal to y minus x, z equal to z minus 1. Whatever it is, your operation. Okay, so that's your program. But in MIPS, it's different. The compiler will decide v equal to s0, w equal to s1, $s1, x equal to $s2, y equal to $s3, z equal to $s4. You name it. And then you write this code. You have a data section, and then you have a text section, and then you have a main program, a kind of function. The colon, and then you put this add immediate as 0, 0, 0, means b equal to 0 actually. So b equal to 0, you have to put this. This S0 is v. Add immediate, then S1 also 1, w equal to 1 means S. See, as we declared here that SW is equal to S1. So here you put 1 to S1, 2 to S2, x equal to y equal to 3, 3 to S3, and 4 to S4. That's how you do it. Add immediate, and you put this number and comma. Okay. So, and then you do this operation add immediate also. You do S4 plus 0 equal to S1. So you put W equal to 0. W equal to 0. W is 1, 0 to 4. And add S1 plus S2 equal to S0. So this is W plus X equal to. Then subtract W minus X. You put S1, S2 to S3. And then add immediate. You put minus 1, Z minus 1 to S4 and comma S4. Then V0, so you put 10 to V0, and then you put a system call. So this 10 to V0 is very important because it's actually an instruction to compiler. It says that this is finished, the code finished, actually, end of the code. So it means the 10 you put in V0 and syscall, and that will end the program. So the program above, like here, integer main void and this thing, you need to write all this code to do that same thing, exactly the same thing. There's a little more instruction, but there is no plus minus sign here. You see that? It's only add immediate, add sub. So this is how you do the plus subtraction addition in MIPS. You have to write this dot data and then some data and then dot text. In this case, we don't have any text, we don't have any data, but then we have this main program. You have all this. Main program is like a function. Program starts here from the main and goes running to the bottom, so top to bottom. Okay, MIPS arithmetic logic instructions. So we declare integer x, y, z in let's say in C, but in for MIPS you put S0, S1, S2 for those x, y, z, and then when you say add, you put S0, S1 plus S2, meaning that all three operands must be registers. Okay, contents of S0 $S0 register S0 equal to contents of $S1 is register S1 plus contents of register S2. So in C, you'd write x equal to y plus z, and in MIPS you write add $S0, $S1, $S2, and subtraction is similar thing. So you put sub SUB is a symbol of subtraction, and you put $S0, $S1, $S2. So some examples here, like how to do add immediate and multiplication, MUL, right? MUL, and that x equal to y times z, you write like this, S0, S1 plus S2. And division also similar way. And remainder, so it's REM is for remainder, so you divide S divided by S1 divided by S2. Whatever result is, you're going to put it on S0. This is how you write it. Y remainder S. So this is the remainder sign. Percent sign, basically. You take the remainder. Load immediate has this kind of symbols, LI, and you put 4 to S0. You have to write this, LI, $S0, 4. A value 4 you putting into S0 registers, x equal to 4, same thing. And move is another command. So operand 1 and operand 2 are any registers, so have to be registers. And then contents of S0 equal to contents of S1. If you want to do that, just say move, like swapping the value from register S1, S0, S1 to S0. Okay. So these are the these are the symbols and simple program for MIPS.
I have a quick question.
Sure.
Is all of the addition and subtraction is only on integers, right? So could we have doubles or no?
It's for integer at this
Okay.
point. For integer numbers, but there is a way to represent the other kind of numbers too. Okay, so that's for integers. Now here the multiplication, also you can say mul S0 times S2 equal to T0. So see, now you see we're using T0 here, T0 and S0. Why T0? Because temporary variable. So when you have a temporary calculation in interim calculation, then you can use, here is your problem, like D, capital D, it's a symbol equal to B, anything, B can be anything, B times B plus 4 times A times C. If you want to do that in C, you can just write like this, it will work. You have a number B, you have a number A, number C, you can get the D. B squared plus 4AC basically. So, but if you want to split this, so you want to do B times B first and put in another temporary variable and 4 times A times C first and then put another variable and then add these two variables together. You can do that too. That's what you could do in here, temp 1 times 0, and it's going to have split it in 3. So A times C, 4 times temp 0, this, that, and then B times B. So they split this in a three three terms, three temporary variables, and then temp1 plus temp0. So in MIPS, you can do that too, but like this. You multiply this, multiply. So you use T0, T0. T0 is a temporary variable, nothing else. And S1, S2, you put it in T1, and then you add T1 plus T0 to S3, and you put it S3. So this is where you write code in MIPS. A little different, okay? It's very different. Very different than C or other language. Now, for input output, so you're getting input from the keyboard or writing output on the screen is very different here. You write very different kind of code. It's not like C out, not like C out or print. It's something. Let's look at that. syscall is executed. So to perform input output, the syscall instruction is used to call system routine. So you have to use the syscall command to get the input and output. Before syscall is executed, $V0 contains a code number to indicate the type of operation. And then $A0 contains additional arguments, we call it argument registers, integer to be printed. Result from user input appear in $V0. So this is the way how they execute. Now, example. Integer n equal to 9. Let's say you assign a variable to n to 9, and then C out, and you put an angle bracket outwards n. So that's how you do in C, and this is how you do in Java, system.out.println. But in MIPS, it's different. The same thing. So you first you say load immediate 1 to V0, like $V0, 1, and then you have to move. You have to move S0 to A0, and then syscall. So if you do that, then computer will be ready to do this for printing a number, it is a number to the screen. Then you do this, and then to getting the input, you put C in, and then angle bracket greater than n. That's in C, programming language or some other scanner system.in. That's the Java. But in MIPS, what do? You have to tell the compiler that type, V0, load immediate, meaning that you want input from the keyboard. And then you put a syscall, and then you move V0 to S0. So then you will be able to get input from the user. And then in terms of a string, if you want to print a string on the output, on the screen, you have to do this. So in C++, you already do you char a string and square bracket equal to whatever string you want to print, and then C out str. And this is like in system.out.print is in Java. And in Python, you just say print and code and put whatever you want to print. But in MIPS, it's very different. So you have to say .data, and then str, that's the string you want to print, colon, .ASCII, you have to write this. And then this is the actual string that you want to print. This is the actual string. You can have a name or whatever. So that's the actual string you want to print with the double quote. You have to write that str colon space .ASCII space, and then quotation, you put that your string that you want to print on the screen. Then you load 4 to V0, load li 4 to V0, and then they're actually giving the instruction to the compiler, that assembler, that we are trying to output something on the screen. And then you put str, you load address, you call it LA, and then you put str to S0, and then syscall. So this will print ABC on the screen. So this code, .data, str colon, space, .ASCII, ABC, and then li, V0, comma 4, LA, A0, comma STR, $0, and syscall. This code will print, this code will print ABC on the screen. This is the string you want to print. You can put your name there, whatever variable you want to print, you use this. Okay?
I have a quick question.
Yeah, sure.
If we scroll up in that page,
Up.
right here, yeah. Why do you have to do syscall? Can you not just do li and then move and then syscall?
No, that's the instructions we need to follow.
Oh,
Syscall first,
okay.
syscall first, and then you move
Oh, okay.
to read integer. To read integer 5 in this case. So int is 5, n is $S0. So the $S0 is your actual number that you want to input.
Oh,
S0 is your actual number. So you're right. V0 to 5, just tell them that, oh, we're trying to get some input.
oh, okay. I get it now.
Then you move.
So basically, you get the input, and then syscall ends that, and then it move basically just assigns the input into S0.
Yeah.
Okay.
So this is how it is. I mean, I can't explain why. This is a single
Okay.
MIPS code. So they have a specific way how to get an integer input and how to get a integer output on the screen and how to write a string output on the screen. They're very specific. So you see that to print a string on the screen, you have to use this MIPS code. .data, str colon, .ASCII, and then your string. And then you put li, $V0, 4, and then LA, $S0, str. That's your actual string that you want to try to print, and then syscall. So it's different for each kind of instruction. So this code, MIPS code, is for writing something on the string on the screen. So that's for that. And then the second one, this one, see, reading input, integer input from the keyboard. You use these 3 lines, li, $V0, 5, syscall, and move S0. S0 is your actual thing that you want to print and get on the keyboard. And $V0 is just a V0 register. So that's for that. And then the first one was for printing integer on the screen. Putting integer on the screen, you have to do li, $V0, 1, move $S0, $S0, and then syscall.
Oh, yeah, that's what I was thinking. Like, if this is printing, oh, okay, I get it now. Because I was talking about, I guess this is what I was talking about. So I guess this is only for printing. Okay.
Printing integer. Printing integer on the screen. And this is getting input from the user, the middle one. And the last one is printing a string on the screen. So they have very specific way to do things.
Yeah, I can see that now.
With the rules, and that's kind of weird, but this is how they do it in MIPS assembly language. Okay, and we'll see more examples in MIPS assembly language and the code, but I think we'll stop here.
Professor.
Yeah.
So which application are we supposed to download for this one?
SPIM. So SPIM is a software. SPIM. SPIM. MIPS simulator. Okay. You need to install this in your computer. I think I already have it in mine. If not, then my other computer will take it up. Yeah, it's somewhere. That's okay. So we'll get that. I think I have it up. Or I have another computer that has it for sure. So you need to download this SPIM, and then am I still sharing? Yeah. So this SPIM. MIPS. Similar to, yeah, we have different language. Yeah, I think there are lots of sources you can get it from, but I think the SourceForce, they have it. Yeah, this one, SourceForce. Yeah, this link you should use, the SourceForce. I'm getting different language. Yeah, SourceForce Builder from SourceForce. That's the right version you download from. Gems allow us download this beam. So download it and install it, or actually it's QTS beam. You can use QTS beam. QTS from this one. You can use this one. This is better. QTS beam. I think you should have QTS beam. Let's see. QT. Yeah, I have it. QTS beam. It looks like this. You see my screen?
Yeah.
Oh,
Yeah, it's weird. It's different, okay? So we have the registers and data and all. Registers. R1, R2, R3, that's the R0. That's the register 1, register 2, register 3, like this 30, 31, up to 31. So they are the registers. And then you have this data, kind of hexadecimal number, this one. And then you have the text, like you type this up. Type this up. And there is a way to load this thing, okay? So we'll look at it maybe next class. So this class we learn a little bit, absorb this thing. This is the console. When you run it, it'll give you the results in this console. So when you run a program. And it's just
But you will go to the overview of this software later in another class, yeah?
yeah, you can so you can download it now and then
I already downloaded, yeah.
you did.
Yeah, just now.
Okay, so this is the you see it's like simple code here. That's load word and add IU of nothing. And this is the actual code you type in. Yes. So this is a particular program it does, but we're not doing this. Okay. So now the so download this beam and read a little bit of the source code. They have a kind of instruction as well, I think, how to program it. But for Mac, I think there is forgot the name. For Mac, you have some other. It's not a Beam, they call it something else. Just can't remember at this point. But I'll let you know. For Mac, they have the different version of this assembly language, the Beam. Okay. So it's a self-contained simulator that runs MIPS MIPS32 program. It reads and executes assembly language program written for this processor. So it's very specific to MIPS processor, the whole language that we learn here, okay? It will not work in any other assembly processor. So SPIM implements almost the entire MIPS32 assembler extended instruction set and all that. Okay, before we go, we have another document you can look at. Yes, let me put that up for you. MIPS reference data. So you need to download this. So MIPS reference data looks like this. Where is it? Maybe here. MIPS, yeah, MIPS green sheet they call it. In the book it has it, but this is the, can you see my screen? So this is the MIPS reference data. You can download from Island, and I put it already. And it has lots of code. Instruction set. You see that? We have add, add, and then you put A, B, D, and then it's R format. So there are different kind of format for each kind of operation. Add immediate unsigned, that add IU, add unsigned, add U, and immediate, this kind of operation. Branch on equal, BEQ, and then jump, Z, and then you have the jump and link, JL, jump register, JR. So all those code you see in this, and it means that hop word, all SH is store hop word, store word is SW, subtract SUB, and they have a format, R equal to R, RD equal to RS, and RT. We'll talk about those later, but we have basic instruction code format, and 3 kind of format. We'll learn about that in details. But this is the sheet you need to look at, do stuff. Okay. So let's just download this and look at that paper. We'll be using that. Okay? We'll be using that. Okay, let's go through the slides that if it is important, I'll let you know what is important, what is not. So here we have branch equal to, means if you want to do some condition, like if something, then do this. In MIPS, it's different. Okay. So that's a simple if statement in C++. So you do if, then you put a parenthesis, x not equal to y, then sum equal to sum plus x, semicolon. So that's your if statement. But suppose x is S0 and y is S1 and sum is S2, because MIPS is different, isn't it? So we write S0, S1, S2 instead of sum equal to sum plus x or y, x, y, and sum. So we need a MIPS conditional branch, they call it. It does different things depending on a test condition. In general, a MIPS conditional branch looks something like, if condition true, go to label, else execute next instruction. Okay. How it works here. You have to write BEQ, branch equal to, then operation 1 and operation 2 and label, like where to go. So what do you want to do in op 1 and op 2? And then you go to the label. If contents of operation 1 equal to contents of OP, the operation 2, then go to label, else execute next instruction. So in MIPS, you do like this. BEQ, S0, S1, label. Mean that if S0 equal to S1, then go to label. Label is anything, any address. So if S0 equal to S1, go to label, else go to next instruction. So this is how you write that. If condition, you write BEQ, like that. It's very weird. Branch, if not equal to, then you have to write leaks BNU, BNE, operation 1 and operation 2, label, meaning that if operation 1 and op 2 is not equal, then go to label. That's all it is. Else, execute instruction. So online, you can write all those 3 lines basically. So in MIPS, how do you write this? So BEQ means what? It's S0 equal to S1, then skip. And what is a skip? It's defined here, next instruction. Else, add S2 and S0 to S2. So S2 plus S0 equal to S2. So you do this in MIPS. So this is how you do the MIPS programming. Making structured flowcharts. So there are some flowchart like in C++, and then I have this jump and conditional go to. I have some example here, if else statement here, if. That's the C program, but then in MIPS, how do you do that? We'll see here. So if num equivalent to max, then flag 1. How do you write this? Like S1 test 0 S0. And what is test 0? Is here. If 0 set 0 equal to S0, then do this. But what is set 0? It's set here. Load 0 to S1. So you can do this like this. So you said, here it says state 0, but then what is state 0? You have to define that. And then what is state 0 here? Then you define that, and then exit. So this is how you write this. If num equivalent to max, then flag equal to 1, else if num not equal to 0, then flag equal to -1, else flag equal to 0. To write this in MIPS, you have to do this. BNE S0 S1 test 0, add I, $S1, $0, 1, Z exit, test 0, BQ, like this. So you have to do this kind of code in C and C++, and this is MIPS. Very different. Okay? You need to go through this a little bit, a few times, and then you will get it. With constant, how do you deal with the constant number? If you put a variable, then how do you do constants? So it's like this. Load -1 to T0, and then you do T0 is skip S0 if T0 equal to skip. But what is a skip? Skip is you define there, not equal to -1, whatever. And then this the branch less than, branch greater than BGT, branch less than equal to, branch greater than equal to. You like this. Like this. It means for S0 less than S1, S0 greater than S1, S0 less than equal to S1, and S0 greater than equal to S1. You read like this for BLT, BGT, BLE, BGE. So this is the condition you need to use when you write AND operation or any operation you want to do, you have to use those instead of C++. Symbols, you have to use this symbol from MIPS. So you have an example here. You have a chart, flow chart here, and then on the right side you have these loops, for loops. How do you use that? For 1, you do that exit for loop iteration. So you write loop like this for 1. Then you have a do while loop. How do you write that while loop in MIPS? It's here. So you write this S0, $0 exit BLE, like branch less than equal to, and then loop, and whatever loop you want to do, and then you have put this $0 loop if branch greater than is 0, and then exit. So this is the exit, and exit is here. So this is how you do the while loop. So like that, do while loop, if then else, it's very different than C++ or C. So here is the logical operational truth table. We need that for the logic design as well. The same truth table we use. So if we have a input Y and Z, like Y is 0, X, Z also 0, then if you do the AND operation, Y and Z will be 0. And if it is 0, 1, then it will be 0, 2. Like if anyone is 0 for AND operation is 0. And 1, 0 also 0, 1, 1, 1. Only time it's 1 when both is 1. So that's for AND operation. OR operation, any one is 1, then it will be 1. And NAND operation, only not AND. So it'll be opposite to AND. 0, 0, 0, 1 should be 1, 1, 1, 0. And NOR is opposite to OR. So it'll be 1, 0, 0, 0. And XOR, exclusive OR. So it's like 0, 1, 1, 0. So this is a truth table. Okay, it could be like 1, 2, 3, 4, 5 table, but we put it in one table. So you can see that AND operation, OR, NAND, NOR, XOR. And then you have this bitwise logical operation. Don't worry too much about this stuff. contents, and no, not much. Then we have shift, another shift operation as well. Shift left. So you're shifting a number, and then it's you shifted that. Shift left, shift right. This is also a command in MIPS. So you move one bit, and then you have this AMP, another operation. Shift right arithmetic, SRA. This is another operation, call it SRA. If you look at that, yes, not very important, but here, you see all this operation format in MIPS, how you do them. Now here it says load immediate, what do you need? You need a operand and you need a value, a constant value. 1, 2, 3, 4, something like that. And move, you need two operand, and you need 3 operand. Actually, all of them should be registered. Sub also need 3 operand, and immediate also need 2 operand and 1 constant. Multiply, you need 3 operand, division 3, remainder 3, and not, you need 2, and you need 3 or 3 operand, NAND 3 operand, not 3 operand, XOR 3 operand, and then shift left. Also, you need 2 operand and 1 value, and then shift right. You need 2 operand and 1 value. SRA also need 2 operand and 1 value. So this is the format you need. And then branch instruction, you need this kind of format. Z, you need a label for jump, and then have a branch equal to, branch not equal to, branch greater than, branch greater than equal to, less than equal to. You need 2 operand and 1 label. Then you need a syscall. So this is basically the code. And then you have some code for the Linux, ls, cat, more, cd, to move from one directory to another directory, copy, move. That's the Linux command. And that's about it in this chapter actually. So how do you start? So you start with the MIPS SPIM or Qt SPIM. Actually, we use Qt SPIM that I already have here. So with this Qt SPIM, and then you write code. I have some code written, so let's load them. Wrote. We have some written there, but I have to find it where they are here. Let's open this test one. What is in it? You put .s. So you load it here and you run using that button. And then you can see. So without looking at this first, we'll go to the file first. So what is in that file? Let's see, where is it? It's 256, test one, twice, 256, and then 256 again. Okay, let's look at that, my C drive. This drive. Let's look at that. So the test one, or this one, open it, Notepad. So this is the code we're running. So what is this? What we're trying to do here? So test one has .data.text main, and then load 1 to v0, load 6 to s0, and then syscall. Then you have load 10 to v0, li, and syscall means it's terminating the program. But here, what are we trying to do here? Load 1 to v0. Load 1 indicating 1. and then loads, and then 6 to A0, load immediate also. A0 should have 6. A0 should have 6. So if you run that, so test 1. Here, I think we have A1, we have this. You can also change. So these are the registers. A1 and A2 have some data. See that? But if we clear this, clear register, and then load A. So you try to load test 1, test 1. Now you can see here. So this is our code. This is our code on the right side. This is our code. So we put 1 to B0, and then put 6 to A0, load immediate. Then we do the syscall, and we terminate the program 10 to B0. And for that, what do we get here in the register? So register A0 should have, so B0 should have 1, and A0 should have 6. So B0, so B0 has 0 here. I don't see any 1. So that's the F. We're not using this, we're using this. So here, A0 has 1, and then you have A1. We're not doing anything with A1 and A2. We put 6 to A0. So here it's 1. Yeah, let's look at the other example, I think. Whatever makes more sense. So let's look at 2. Let's look at 2. What is in 2? Open this. This is bigger. So we have dot data, then name, colon. So that's the string, dot ASCII Z. And then I put my name is Abdur, whatever, and the course, dot ASCII Z. So here we're trying to do what? We're trying to do this string on the screen, my name and course number. And then dot text, have nothing, and then we have a main program. So what are we doing here? Loading 4 to V0, meaning that we're telling the compiler that we're trying to load a string on the screen. And then LA, we put name, comma to A0, and then syscall. And then again, we put 4 to V0, and course is another string. So try to load that, load LA, A0 point. And then we put 7 to S1. So we load immediate, so S1 will contain 7, that's the number. And then 1 to V0, load immediate. Then we're moving that S1 to S0 and syscall. Then we load 5 to V0, telling that we're trying to print it. 5 is for what? Remember that? 5 is for.
Isn't it displaying it on the screen or something?
Yeah, so let's see. I can't remember, but we have it here. 5 is for. Yeah, you can remember all those things, like what number is for what. It's kind of weird, not to remember, but you can look at the manual. Did I pass those? No, here. So 4 is for something. It's up here. I think it's after this, after the program. Yeah, 3 of them side by side, as examples. Yeah. Here you see, pipe, loading pipe to V0 is for what? For reading integer. Reading integer. Yeah, like this, reading integer, like getting input, actually, getting input, integer input. So loading pipe. So this program here, when you load pipe, means we're trying to get input, the integer input, the V0 and S0. So S0, we're going to get S0. And then 10 to V0 is ending the program. So let's run this and see what we get. We're supposed to get name, course number, and 7, and display that on the screen, actually. Input. We type something and then get the input on the screen. So let's do that. So that's the test 2. So that's the program name is test 2. So let's clear the register, reinitialize simulator, reinitialize it. So you got 0. Then we load file. We do test 2, I think. So test 2, open it. So now it's loaded. We can see that here it's loaded. Here for to V0, name A0LA syscall, port to V0 again, course. So this is our code that we wrote. Okay, fine. Now we run it. Now you should see that on console. Yeah, here it is. See, in the console, you can see my name is Abdur, course name is 256, and it's 7 as the input, because I put it there 7 particularly plus 0, and we're going to display it on the screen. See that? So this output you get for this code. So you get name and course and this 7 on the screen. And to get that, you have to write all this code and end the program. Load 10 to V0, and then you end the program. Play with this, okay? You download this and write some code like this from the PDF or from the book or PDF version of the book, and try this. And there are some example in the YouTube. You can probably look at it. Okay, there's some examples in YouTube. So if you're interested, you can learn there. So bottom line is, what are we trying to do here? We're trying to learn how to program in MIPS. So they use symbols rather than high-level language. So this is a different language, and it will take time to get familiar with it and learn. Okay, so don't get scared that it's too hard, but it's not really too hard. It's just you have to follow the syntax, whatever the MIPS provide. Whatever syntax they give us, we try that. And it's very specific to a process. Assembly language is very specific to a particular assembler. If you write code in one, it will not work in another. It's not like Java code that you run in any machine, it will work. No. So it's very specific to a CPU, and you have to follow exactly what the syntax is for that particular programming language. So here, programming language is MIPS, and CPU also MIPS, so we try to do that. And this is like a not actual CPU we're working on. We are working on a simulation environment. So this MIPS, they make whatever environment we have, that's a simulation. That's not a real time. They're not getting access to our CPU and do this kind of stuff. So this is a real time, and this is a simulation environment. So we have downloaded this Qt Spin. Any question? Try to learn that what this Qt Spin, how to use this. So it will help. Then you have this about Qt Spin. So there are some links, source ports, and they give you some public license. You can try that. 2020, January 2020 version. So I downloaded. What this help? Yeah, they have kind of a manual. So you can, so Qt Spin manual. Getting started, loading a program, running a program. Yeah, they have all that. So go there and try to follow this instruction. Getting started with Qt Spin, it opens a window containing that looks like the one below. And we already seen that. And then Qt Spin's main window has 3 parts. Narrow pane on the left can display integer or floating point registers. And the white pane on the right can display the text segment, which contains instructions on the data segments. Choose between text and data by clicking the tab at the top of the pane. The small pane on the bottom is where Qt Spin writes its messages. All of the pane are dockable, which means that you can grab a pen by its top bar and drag it out of Qt Spin's main window to put it on some other part of your screen. Qt Spin also opens another window called console that displays output from your program. So you can read this in the manual a little bit and learn how to do this stuff. So you see that your program should be stored in a file. Assembly code files usually have the extension .s. So file1.s. To load a file, go to File menu, select Load File. The screen will change as the file is loaded. To show, so another press File menu, slash and load. The kind of stuff that I already showed you. Running a program, to start a program. Running after you have loaded it. Go to the simulator menu and click Run, Continue. You can step into it too, into the program. Set breakpoint, simulator pause, kind of stuff. Display option, changing register and memory, settings, MIPS, Qt Spin, and I have the and then I have the following program. Yeah, it's same thing. It doesn't have much. Pretty. Then you have this assembler linker and spin. I don't need this. Yeah, it's pretty simple actually. It's very basic stuff to write into. It's not very good to write real code. This is just for the simulation environment is just to learn how to do. But other programming like assembly language probably better, and you can use real-time CPU from your computer and work with it. But this one is just a simulation, and just to have a test how the assembly language, especially MIPS, can be used. Okay. Any question? So basically, we're learning a new programming language, a new language, of course, as we see that is very different than high-level language, and use the hexadecimal thing, and I'm not going a lot of things with hexadecimal numbers, but just to give an idea that how this assembly language can be programmed. It was very different than normal high-level language. You can see that for loop, while loop, and input output, if else, is very different compared to high-level language. So this is the important part we need to focus of these parts: control unit, registers, main memory, arithmetic logic unit, program counter. So this is the one you need to be familiar with it and understand the definition. You may have a short question. And we may have some exercise as well for the writing the assembly code and using MIPS. That simulator, but I'll give you a very simple one, not very complicated one. Okay. And you need to get familiar with this, this book, the green sheet that I showed you. Sun Island. Oh. Green. Let's load this thing. Yes. Here somewhere. I already opened it. It's on the islands. It's in the slides too. Yeah, the green sheet. This. We'll be very familiar with this, and once we go to the further chapters, but you see that here, all this operation given, opcode, learn about those, but and there's some explanation what this code, the assembly code does. Load word, you have a load word, and you have this particular format to follow that, and then you have this opcode and function code. We'll learn that very shortly. Opcode and function code, what does it mean in our the other slide? Let's see. Slide. So chapter 3 slides. So we talk about pointers and arrays here, but we'll test it, pointers and arrays, but we'll not give you like the serious assignment on this pointers and arrays, but we'll have some idea how these pointers and arrays you can deal with in these MIPS. Yeah, I will skip a lot of slides that you don't have to go through, but I'll give you some slides like pointers. Pointer is a variable that contains the address of another variable in memory. So that's the C++. We have this. C. You have these pointers, and here they use pointers as well. But you see that in modern programming language, like Python, you don't have to worry about pointers at all. So it deals with the interpreter itself. So the idea about pointers is gone. In Java, you don't have to worry about it. Memory allocation and all that. It deals with the compiler itself. But this assembly language still you need to deal with the pointers and other stuff. So we learn a little bit about pointers, and then pointer operation. Yeah, we'll go through it probably in the next class. So for this class, I think you should focus on the spin and all these slides we have on the on the chapter 2. Chapter 2. And go through this definition. The definition is important because you have in the quiz. In the meantime, probably I'll give you the assignment for the first 2 chapters that we covered. The conversion from binary decimal, decimal binary, binary hexadecimal, hexadecimal to binary, and decimal to hexadecimal. That kind of conversion thing. And maybe some binary addition, subtraction, that kind of assignment, okay? Any question for a particular thing? So now you need to download, if you have not, the QtSpim from SourceForge site, and then start playing with that, okay? And you have a manual there, so you can play with that from the manual. The manual I showed you there. Little manual there on the help, view help, and the manual. QtSpim manual. So again, go through this. I have some idea, and I showed you that. So you open a notepad and write the code and save it as .s extension, .s. As I have my files, I saved it and .x extension, you see that. And then you can go to Spim and open it. Open that file from here, load file, operation. Then, so it comes up here, .s extension. So you can have quite a few examples here, but some of them doesn't work. I don't know why, but that one worked. So you have some console and you have some result in the console. So you go through the manual and start writing some simple code, add 2 numbers, multiply 2 numbers, that kind of thing. You can do it easily. So you can load immediate and then just add some numbers. And you can print it on the screen using those code. So that's the kind of hard part to remember. What to load immediate to get what? Like getting input from the keyboard, printing, and things on the screen, that kind of stuff. So this concept is very important too. So you're going to go through this. The control unit, arithmetic logic unit, registers, program counter, this definition. And then register has this 0 to 31. As you see that here as well. So we have 0, so this is the register, 0 to, see that, 31. So this is correspond to that, register 0 to 31, 32 registers. Registers is the array of 32 bits basically. So each register has 32 bits, this is 30 bits. There are 31 and 32 of them. Then some of them especially can use 1 and 0, but the rest you can use and have different name. And as I said, we're going to use this. Let's see. And then I closed again the manual, the green paper. It's in the bottom, on the right side, the first page. You see that here, $V0 to V1, 223 number. And then you have say $A0 to A3, 427, like integer number. And R0, P0 to 7, 8 to 15, temporary variable. S0, S7, 16 to 23. Yeah, this is the important thing. Stack pointer 29, and then FP floating pointer is 30, or A. So those the numbers correspond to these registers. So we'll learn that because we need to convert from MIPS language to machine language, and machine language to MIPS language. that time we will be using this table. This, when you have 4, means A0 to A3, A0, so the register A0 for 4. So we'll learn that. So just get familiar with this a little bit and look at the all these pointers, and especially this. I think if you remember that which number load immediate will give you what on the screen. So that here. So when you load 1, meaning that you're printing integer on the screen. Load 1 to V0, load immediate, LI. Then you move S0 to A0, then syscall. This will allow you to print integer on the screen, like we did print 7 on the screen, in our case, in our test 2, I think, it's gone, so let's run it again. So the test 2, let's run it again. Clear the register, reinitialize simulator, and reinitialize and load. I think we did test 2, and test 2, and load it, and run it. Now we'll see the console. Console show there. Yeah. So you see the 7 get displayed there, and before we display 7, what do we did? You see that here. So we put 1 to V0, and then so we load 7 to S1 first, and then we put 1 to V0. Means I'm telling that we are trying to write a integer output on the screen, like 7, and then we move that, and then syscall it. So this gives you that output on the screen, the 7, okay? And then we put 5 to V0, and we syscall as well, meaning that, so what does it mean? The 5 to V0 means what? Here. Reading integer from the keyboard. So you have to say 5 to V0, and then you move. So you have to have both command there. And that's what we had there. 5 to V0 syscall. Then V0 to 10 to V0 is terminating the program. All right, so that's your job now, to look at this, get familiar with this page and this, and go through this few times, try to get it, how they get input from the keyboard, or integer number on the screen, and the string on the screen. So string on the screen, how they do that, and you get familiar with this. String to the screen, you need to write this dot data, str colon stora skiz, ABC, that's your string, and then V0, 4 to V0, and then str load address, A0, and syscall. This will give you string on the screen. That's how we did on that program. Okay. So yeah, try to get familiar with this, the jargon, the symbol of assembly language, download QtSpim, and look at that manual, and try to write program, any notepad, and save as .s extension, and then load it from the QtSpim, and then that will give you some output when you run it. All right. Any question? Any question? Have 14 students? Why? Then I should. So, are we done over time? Or what? I think we're done over time.
Yeah, it's 5:13.
Huh? Oh my God, I have the next class. You didn't tell me anything.
Sorry, I wasn't sure if it was on purpose or not. I didn't want to